here, right? So it means that at this point it wants to ramp up, the phase up to 1 decade after and then keep it constant, right? That's the impact of this pole, which starts from 1 decade before till 1 decade after, right? So again, if we didn't have this, then these two up to this point would cancel out, right? And then we would have a ramp here and then stay constant. So let's actually add these two up to this point, right? So up to this point, let's just like add these two. Okay, so like we're not gonna include the impact of this pole for now. Let's just add these two. So if I add these two, this is like up to this point, we have two forces against each other, but they're exactly equal forces. So they're gonna cancel out. Right, so it's gonna be like this. It's gonna be constant at negative 45 degrees, right? Then at this point, this pole doesn't have any impact on the phase anymore, but this zero does, right? It tries to increase the increase the phase by the 45 degrees ramp per decade ramp, and then after that it is gonna stay constant. Okay, so this is what we have so far for the impact of the pole and zero, one pole and 1 0. Okay, but I didn't include the impact of this one. What is the impact of this one again? The impact of this one starts from 1 decade before and it's gonna last until 1 decade after. So it means that it wants to start from here and it wants to go up to here and then stay constant. So up to here, this is gonna be negative 90. So now again, we have an impact of this. I should have done this like different colors. So this is green, which is this one, and this is red, which is this one, and this is blue, which is this one. So now again, we have two forces fighting each other, right? So at this point up to here, from 10 to 100, they have the same ramp, but in the opposite order, so they're gonna cancel out. But at this point, then this zero doesn't have any impact anymore, but this one still has one more decade. So it means that at this point, it's gonna go down with the slope of negative 45 degrees per decade. And then 1 decade after, it's gonna lose its impact, right? So at omega equal to 90, what's gonna happen? At omega equal to infinity, what's gonna be the phase? It's gonna be negative 90. Okay. So that's basically what we have to do to draw the Bode plot, both magnitude and phase. Okay, this was a very challenging example because you saw that the impact of this one and this one overlap, the impact of this one and this one overlap, right? So that's why I said like maybe it's not a good example to start, but now like when you see this one, if you understand this one, you can do any other Bode plot. Okay, I want to show you, I want to verify why the phase at omega equal to infinity, as omega approaches infinity, it's going to be negative 90. So let's look at this one. if omega approaches infinity, we can ignore this one compared to infinity. We can ignore this one compared to infinity. We can ignore this one compared to infinity, right? And then we can cancel one of these j omegas with this one. So we would have 100 divided by j omega. What's the phase of 100? It's 0. What's the phase of j omega? It is 90, right? And the phase of the transfer function becomes the phase of numerator minus phase of the denominator. So that's just to verify that we did it correctly. Okay, so this is how you do Bode plot for both magnitude and phase. Now I want to do one more thing and then finish this series of videos. So I want to analyze this circuit for you. Let's actually do this one. Okay, this is one of the circuits you have, so let's analyze it. Again, this is negative feedback, so this is virtual ground. I can just let's call this one R and this one C. So then this would be the current that goes here. It's going to be V in divided by 1 over j omega C, and it's going to be equal to 0 minus VO divided by R. Okay, so now if I want to find VO, let me simplify this. It means that j omega C times VI, it's going to be equal to negative VO divided by R. So what is the transfer function? H of j omega. If I define it as VO over VI, it's going to be equal to negative j omega R C. Okay. And you guys know that if you have j omega, this is like in the frequency domain. In the time domain, this represents derivative, right? So it means that basically if I say VO is equal to negative j omega RC VI, this is just like a constant, right? But j omega, this part, means that in time domain, it means that VO of t is equal to negative RC dVi by dt. Okay, so that's basically what's happening here, right? You've seen this before. So that's why this is called this is a differentiator. This circuit, it's a differentiator. Now, so in many examples, in many applications, you need to take a derivative of a signal, right? So we can use this circuit. But this circuit has one problem. Let's look at its Bode plot. So what was the transfer function?